All right. So regarding the tasks, we have a general kind of description, and we will practice multiple skills, as I told you. Like we will practice some of the ciphers, we will use GPG and some SSH keys. So it's all here with some instructions of like what to do and what the keys are for and so on. Of course, we're not going to memorize all of this. We will use the man pages and the help for different commands, but we will memorize some commands like, OpenSSL. Like you should kind of remember that there is command like this and for what it does, right? So that is sort of something you will have to memorize. But all those parameters, I don't remember all those parameters. I always have to look it up, right? So there is no point you memorizing it. So then there are a couple of tasks. Some tasks in the middle I am still working on, so I will kind of finish it and post it here. And then there is this final checklist. So this, like we have to have like an oblique. And I told you we're gonna have two obliques, one for this week and one for next week, one for crypto and one for blockchain. And then for crypto, it's sort of here. So please read this and kind of think about it. So it has a couple of modules. It has like the classical ciphers to use OpenSSL and to do some small things with it, to do some small things with hashing and with symmetric encryption, with PGP and email, and then SSH and some automation with some of the command line tools, right? So it has quite a lot. So it has 14 points. And I said here, just do 7. You pick which ones and just do 7, okay? And then how you should do it. And I suggest you basically like start recording yourself and just start doing them, like type it and so on, like record yourself. It will be like a short video. Um, we could do it that you don't record the video, that you sort of do it and then send me a PDF file with the results or description of how you've done it. But then it's a little bit um, difficult to make sure that it has not been done by bots. If you record what you're doing, then of course you can prepare yourself with the bots and then you still has to do it, right? So at least I know that you type the commands, right? So it's a little bit safer. I mean, I don't care too much. Like what I care is that you learn and you practice it. So if I like, and like all of this is just for an oblique, like you will have to do exam anyway, right? So this is like pass fail kind of thing. Like you have to do it and that's it. Like I'm not grading it, right? Um, so I think it's sort of reasonable. What do you think? You can read this. Like you don't have to answer right now. We can discuss it after the break. So, but have a look and think about it. Like how should we do it? I think like doing the short video is okay. 7 out of 14 is also probably fine. You can cherry pick which ones you already know and just do that. So it will be sort of easy. And the rest you can do later. For the exam, we will probably cover most of it, right? So we probably will cover like 10 out of 14 or something like that. So some of the things that you will do now will be basically the same for the exam, right? So, I mean, it's like at some point you will have to do it. I don't think I will have all of them because then the exam would be really big because we have to do something with the blockchains as well. So this is covering the first half of the course and then the other one will cover the second half of the course. The second half of the course for me is more fun. So, but this one is a bit of a prerequisite. So check it out. One interesting thing that I think you might like is there is some extra things about Tmux. Who is using Tmux? You're not using it, so yeah, that might be fun for you. Tmux is some like a terminal multiplexer, which allows you, it's kind of like screen. So it allows you to run jobs, kind of put it aside, log out, log in back, and bring it back. So it's sort of like you never end the session. It's always there, and you can have multiple tabs and multiple split windows. So you can see it here. I have multiple tabs. I can switch between the tabs. I can change the I can change, I can search, and I can, where is the, let me see. I can split, oh shit. I can split the screen and have multiple screens in the console, and I can easily navigate between them. So I can sort of do like, it's sort of like a terminal multiplexer. So it sort of streamlines your work and makes your work with terminals a little bit more productive. But it's like, yes, you can do it with like terminal windows and so on. But this one is a little bit more like heavy duty tool. Like if you are DevOps, you're probably gonna use it most of the time, right? And it also allows you to run something and then put it into like background, close everything, and then restart it, and it kind of refreshes the sessions. So sometimes when you log into a server and you close the lid, the connection is broken, and the server, whatever it was doing, will stop because it doesn't have the pipe. So then this one kind of keeps the pipe open even if you close the lid, right? So it sort of pretends that the connections are still working. Yeah, you can try it out. You don't have to. This one is optional. What we also will do, let me check this one. We do very simple things. Word count. I don't know if you used word count, but it's sort of a useful command. Cat. Yeah, permissions, of course, we kind of talked about it. And then we talked about some of the controllers. And then the next one is about find, grep, and oak. Many students don't, like, they know about find or grep, but they don't use it. Have you used find or grep? Yeah, it's super helpful for some processing of data. And then oak, do you know oak? This one? So this one is for processing structured data. Anything that is comma separated value or logs or anything, this tool is excellent because it knows about the syntax of columns and rows, and you can write like a one-liner to calculate averages or to cherry pick something from the logs and so on. So there is a task which kind of talks about this, and you can practice a little bit. So then we also talk about like piping. So like doing this sort of combining something with the pipe, and tail and head with line numbers, and sort and head and so on. So it's like, how can you get something done without writing like Python script or writing something kind of heavy, right? It's just command line kind of tooling. So many of them are available, and many of them allow you to process text files. And in like cyber analysis and so on, we often deal with logs or traces or some dumps, and then those tools are super helpful. So some of them are kind of discussed in this and the next task. So as I said, most of that was probably familiar to you, which is fine. Just gloss over it. Some of it, if you haven't practiced it, you can kind of cherry pick and do something that you haven't practiced so much. The editor, I don't care, like whatever editor you're using. If you're not using Vim, that's fine. You use whatever you use. But knowing Vim is kind of, especially if you're working with crypto, in a sense of security, cyber, it's very useful because often you log into a server and there is no other editor. It's only Vim. And then what? Then you're stuck, right? If you only know Nano or something else, you cannot edit stuff, like, and it really handicaps you, right? So I'm not saying you have to be a Vim ninja, but you just need to know like how to open it, how to edit stuff, and how to save it and close it. Like it's just like 4 or 5 commands that you kind of need to know. And then it's fine. Like you don't have to be like super ninja in Vim. You just know the basics, and then like the 2 modes, and then the rest, it doesn't matter. Like if you're not super efficient, then fine. But at least you can open Vim, edit something, and go out of it, right? So the basic of Vim, I think you all should know. And then the pipes. So pipes are super nice with the error pass, like and so on. So I probably you all know this, but just a refresher. So some of it is just a refresher. Some of the later ones are a little bit more advanced. So what else do we have? We have the PGP keys. As I said, we will use pretty good privacy for generating our keys and doing some offline and through the email client. Not email client supported natively. Like, for example, Outlook does not support it natively. Why would you think Microsoft don't want Outlook to support pretty good privacy natively? Any ideas? It's like one of the major like email clients and it doesn't support it. It never supported it and it will probably never support it. Why is that? No ideas? All right, so like think about it. Funny thing Microsoft was pushing is this concept of end-to-end encryption. So what is end-to-end encryption? If you have a messenger, how does that work? If I have two people and they use some sort of a communicator, right? So they use like a communicator of some sort. What does it mean to have end-to-end encryption? Yep. Any ideas? Yep. Yep. So there is a message. The message is encrypted. It kind of goes here, and then the message is decrypted, and this person reads it, right? And that means end to end, right? So that's what it normally means for normal people. For Microsoft, what end to end means is they have a server in the middle. This person encrypts it. It gets to here. Then it's decrypted. And this server encrypts it and sends it to this person. And this person decrypts it. And they call it end-to-end encrypted. And who the hell is this? It's Microsoft, right? Right in the middle. So they say, yeah, it is end-to-end to us, and then end-to-end to the end user. It's just happened. We are in the middle, and we sort of, doing the looking into the message. So they advertised end-to-end encryption like this, and then there was like a community outrage, like saying, no, come on, that's not end-to-end. Like you're really misusing the term end-to-end encryption for your whatever tools Microsoft offers as a communicator, right? So Microsoft is super weird. With the other big companies, they actually played fair. So when Facebook announced they have like an end-to-end encryption in Messenger, it actually was end-to-end, right? It actually Facebook didn't have access to your messages. I mean, they still do because if there is a human and there is a phone and there is a place where the message gets encrypted, at some point the message is plain text, right? So this part is secure. Like after this is encrypted and to that point where it's decrypted, okay, so decrypted, so that part is secure, like nobody actually knows what the message is. But once it is decrypted, it is a plain text again, right? So, so the person who is reading it and the person who is writing it, at some point on your device, the message is plain text. And who has access to that plain text? Well, whoever is giving you that app or whoever kind of exploited your phone, right? So even if you have end-to-end encryption, it does not mean you are like secure because there is some vulnerabilities and some like possibilities of somebody getting access to your messages on the ends, on before they are actually encrypted. Nobody can kind of sneak out in the middle and observe and know what you are talking about. Like this is eliminated by end-to-end encryption, but this is still a real threat, right? So that's why operating systems like Graphene OS for Pixel exist, because they make your phone so secure that nobody actually can see that plain text And then you have a kind of enhanced security, right? Anyone using Graphene OS? You use? Yeah. How usable is it, like in day-to-day life? Okay. Yeah. Okay. Yeah. Um, yeah. I didn't hear about it. Okay. Yeah. All right. So I kind of diverged to Oak from Oak to some other topics, but the idea is that we are gonna practice some things, and then, as I say, you don't have to practice everything. You just cherry pick what you haven't used before, and then you kind of practice that, right? Um, Okay, I will finish the remaining tasks, which are kind of not here, because I have to clear, like, just check that, like, there is a little bit of Python code and so on. So I just need to make sure that it is sort of what I want from last year and from what it is, what's there. So I will post it once I kind of finish it. And these ones are pretty finished, so you can already start doing them. You do need to have access to Linux. Um, if you're on Mac, you probably can run most of it on Mac because of the brew and all the tooling for Bash and command line. But if you're on Windows, you definitely need Linux, right? So you can see how far you can get on Mac if you are on Mac, and then you probably should have a VM. Also, having VM allows you to set up like a Git server, so then you can play with Git yourself as well on like having a local repository on your partition, and then having kind of a Git server to which you push and pull from. Okay, so any questions about that? There might be questions about the scope of this first task, this first oblique. So think about it and check this final checklist. Um, right. So then I will go and open basic PDF. So I will make. Okay, so we finished yesterday. Yeah, we finished yesterday. Yeah, OTP, you kind of need to remember the concept of OTP. It comes handy later. Um, yeah, we talked a little bit about those. We will talk about them a bit more. Yeah, so we pretty much finished here. So symmetric encryption. Um, so in this section, we will cover classical ciphers, which are using symmetric encryption. And we will use some of the examples that we already discussed yesterday to some extent. And then we will dive a little bit more into the block ciphers and talk about the limitations of DES and like that, why, for example, 2DES does not really make sense. And then a modern incarnation of the symmetric keys with American encryption standard. So symmetric, we talked about it yesterday. Very simple concept. You just have a single key. You have to share this key somehow with the parties, and then you and the recipient basically sharing the same key. And most historically, we have been doing symmetric cryptography until 1970s, right? And it was also a kind of a funny story because um the mathematician who discovered or invented the RAS R, uh, RCA algorithm, he like was told that he should not make it public. Like the government didn't really like the idea of asymmetric cryptography being widely used. So I will pause. Diverging. So anyway, the algorithm is out and people are using it. Some jurisdictions are still very unhappy, and US is one of them, and they still treat very long keys as a special case, and it's sort of, complicated. So we have 4 ingredients. We have plain text, encryption, decryption algorithms, and then we have a single secret key and the ciphertext. So in 70s, we migrated out of the symmetric keys, but symmetric keys have a lot of advantages. One advantage of symmetric keys is that it tends to be much faster than asymmetric key cryptography, which means if you have to transfer something for stream ciphers, we predominantly use symmetric keys. We may use asymmetric to establish the channel, the secret channel, the handshake, and then we're gonna send a shared key and we're gonna stream stuff using a shared key. That's usually the typical pattern because it's very efficient. It's much more efficient to use symmetric cryptography. All right, so then the picture is quite simple. We have a plain text input with the key. The key on the encryption and decryption is the same. And mathematically, we say the encryption algorithm uses the key and the plain text and produces the ciphertext. And then on the receiving end, we say we have a decryption function, which takes the key and the ciphertext and produces the original message. So this X and this X are the same. It's the original message. And this Y and this Y are the same. This is the ciphertext. No magic here. So there are 2 requirements. So one requirement is that the attacker should not be able to decrypt ciphertext, even if he possesses a number of ciphertexts together with the plain text that produced it, right? So that's a strong encryption algorithm. We have encryption algorithms like the Caesar cipher, and with the Caesar cipher, if I give you a plain text and the ciphertext, you immediately know what the key is, right? You can calculate what's the offset, right? That means it is still an encryption algorithm. It's just that it is not strong, right? A strong one would not allow you to quickly do this. So this is a little bit of a theoretical concept because we always working out of how to break the current encryption algorithms, and we are measuring how strong they are. The longer they last, the stronger they are, right? Because we were not able to break them, right? And the secret key must be known only to the sender and receiver. So you have to somehow share it between the sender and the receiver. And then there is this mathematical notation that we often use for describing what's going on. So then cryptanalysis is the science of trying to work out what is going on between the plain text and the ciphertext, and what are the properties of the ciphertext that are leaking such that we can work out something. We can work out some information about the length of the key or the structure of the key or how the algorithm works. I mean, algorithm we already know, like, but the structure of the key basically. And then once we crack the key, then it all is cracked. So all the past encrypted messages and all the future ones are sort of for you to see. So you're exploiting the weaknesses in the algorithm. You can assume that the attacker and the person doing the cryptanalysis knows the algorithm, okay? So there are different ways for conducting the crypto analysis, and we will dive a little bit more into them. But this is like we're trying to be smart, and we're trying not to do a full search space search, right? because the search space is so big that we're gonna be either unable to do it or wasting a lot of resources. So cryptanalysis is trying to kind of work out some heuristics and some mechanisms for us to know something about the key without doing a full-blown brute force attack. And then the brute force means we systematically check every possible combination of the key, and eventually we're gonna find what key was used, right? The longer the key, the longer it will take to systematically go over all possible keys. And then it also means some key lengths are impractical. Like it takes so long that we're not gonna be able to do it in the lifetime, right? Which is sort of an interesting, which is kind of an interesting race, because let's say you want to encrypt your hard drive, right? And you want to do it in an efficient way. So you say you have to set like a goal. So you say, I'm encrypting my hard drive and I don't care if it gets broken after 50 years, okay? So 50 years is your window, but you're using the current day capabilities of how long it will take to break the whatever you're doing, whatever the key length is and so on, right? But the technology progresses and we have a speed up. So things kind of speed up. And we can crack today things that we couldn't crack like 10 years ago because we have more computational capabilities, right? So then you need a buffer. So you say, okay, I want to protect it for 50 years plus a little bit of a buffer for these improvements, right? So that's one angle. The other angle is we also want to be quantum resistant, right? So we also want to protect our hard drive such that if there is like a breakthrough in quantum cryptography or quantum computing, like in 2 years, our hard drive is not gonna get cracked in 3 years, right? So we want something that is quantum resistant. We're gonna talk a little bit about quantum resistance later, but some algorithms are by nature quantum resistant, and that's fine. Some are not. And most of the ones which are relying on factorization are not quantum resistant, because factorization is one of the computations that quantum computers are actually really good at, factorizing large prime numbers. So we need to consider those factors when we are trying to defend ourselves against brute force attacks. But trying to prevent crypto-analytic attacks is a little bit difficult. It's kind of beyond the user control. Like the user controls the size of the key. So you sort of say, okay, what is the search space for the brute force attacks? But this one is a kind of a science for experts. Like and normal users cannot control that. So some algorithms are stronger than others, and it's the scientists who kind of define which ones are more likely to be broken or less likely to be broken, right? Okay, so what do we rely on? The nature of the algorithm itself. So we're gonna look inside some of the algorithms to get a feel, but the intuition is that the algorithm works out how to convert something into something else, and it has certain structure. And if the structure is cyclic, it will be visible in the ciphertext. Or if the structure reuses something, it may be also visible in the ciphertext. So you can exploit some of the ways the algorithm works, and also the designers of the encryption algorithms, they know it. So they sort of try to diffuse the information that is happening in such a way that it's harder to do that. You need to know a little bit about the plain text. Like it's different if you're analyzing English text, and it's different if you're analyzing encrypted hard drive with binary blobs, right? The characteristics of the data is completely different. So then the characteristics of the ciphertext are also different. So you need to know what is it that you are cracking or you are analyzing, right? When they were cracking Enigma, they knew the messages from German militaries, they are always in German. They could assume the communication is in German, right? And they also assume that, like they've observed that at the beginning or at the end, often messages start or end with Hi Hitler, right? The greeting. So maybe there is some kind of regularity. Maybe the messages have a date, right? And then you can sort of brute force some of the date assumptions about the messages. So you need to know a little bit about what it is that you're trying to break. So you need to have some knowledge about the plain text. And then it's very good if you have some pairs, right? If you have a plain text message and the encrypted message, if you can sort of see them side by side, you can work out some of the properties. For Caesar and encryption, like Caesar one, if I have just one sample, it's cracked, right? If I get one encrypted message and one plain text message, like it's obvious, right? For some algorithms, you have more, you have multiples. And as I told you for web, you need to have quite a lot of samples, but you get enough, like if you get enough samples, you get some statistical frequency analysis, and then you can sort of work out what the key is, because it's very like improbable that the key is different to what you think the key is based on those statistics, right? The statistics is pushing you to like an attractor, and that attractor kind of reveals what the key is. So then once you crack the key, yes, as we said, all future messages are broken. So there are 5 different ways the crypto analyst analyzes the algorithm. The first one is you only get the ciphertext, okay? So you are kind of, you need to crack something, and all you got is a ciphertext. That's the hardest one, right? You have nothing else to go with, right? So the only thing that you have is some guesses. So if we're talking about Caesar cipher and you only got ciphertext, then you're sort of thinking, okay, maybe it is a Caesar text, right? You're making an assumption. You don't know if it is Caesar or not, but you have to make some assumptions. So if you have some text, I don't know, like this, and then you sort of like, okay, what is it? I don't know. Maybe it is a Caesar. So then if you assume this, you can do a brute force attack and kind of do all the possible shifts and see if this one, let's say it's a kind of longer message, works out into something in English or some like human language, right? If you hit, like you usually have like an alphabet of 24 shifts to try, and then or like maybe a little bit more if you use special characters, then you will crack it. But you've tried everything, turns out no, it was not Caesar, it's something else, right? So your hypothesis failed, you have to try something else. So this one is the hardest because you have to make a lot of assumptions, right? Okay, so then you have a pair. You not only have a ciphertext, but you have a pair of a ciphertext together with the plain text. And that gives you much more information, right? Because you can see the alphabets, you can see what is being used on the entry, what symbols you have on the exit, what are the patterns, like if it is an English text, you can analyze the frequency of the letters, you can analyze the frequency of the letters on the ciphertext, and so on. You have much more to go with. So this one is quite good, much stronger than this one. But it's given to you. So maybe you have like 3 samples and they resonate around the same sort of attractor. And even though you have 3 samples, they don't really reveal too much about the key structure, right? So maybe what would you like is you would like to define your own plaintext and see what the encrypted message is, right? And so that's the next step. So this one, you are given some encrypted text and plain text. With this one, you're injecting the plain text and you're seeing how it looks like encrypted, right? So you know, like you can choose what it is, and you can choose something with regularity, with certain patterns, and see how those patterns appear in the encryption, right? So you choosing what you put in and then you observe what you get out. So as I said, originally you might get something with no patterns, and it doesn't give you much. But then what you can do is you can feed it with different patterns, like on the plain text side, and then you observe what it leads to on the ciphertext, and then you can see if those things influence the patterns here, and you can work out, okay, I can work out some statistics, right? So you can feed certain characters with certain frequency and then observe it is reflected here. Or you can feed certain cyclic patterns and observe if the cycles sort of appear here and so on. So this one is like already super nice, right? And this one is used for a lot of Wi-Fi cracking, because what you can do is you can like join a Wi-Fi and sort of start emitting traffic, and you know what you are emitting. So then you can see what it is, how it is encrypted, right? And then, yes, you get the point. So then there are two more, kind of like symmetric to this one. So from this, we know that this one is currently the best for us, right? We can define our own plain text and see what is the ciphertext. There is a symmetric to this one, which is that one. So you not only can feed plain text and see what the ciphertext is, you can have some hypothesis about the encryption, and you can choose the ciphertext and see if it decrypts to something meaningful. How would that work? Usually you have some form of mechanism to, because like how would you, like if you like with the plain text and encryption for the key that you're trying to crack, it makes sense, right? You don't know the key and then you are kind of feeding it forward, but like when the algorithm feeds it back, it feels kind of unusual. But you can, like, there are some mechanisms to do that. So what you're doing is you're kind of feeding the ciphertext and you're observing what the plain text is, right? Normally you sort of don't see that, because like if you don't know the key, you cannot fool the system to do it for you. So you have to have some special arrangement, like to achieve this, you have to have like a special arrangement for what it is that you're doing, right? And then the final one is both. So that the final one is either way. You can either do it forward or you can do it backwards, but you can do it at your will. So you're choosing both cipher and plain text, and you kind of navigating the space both ways, right? So it is kind of important, because we almost always think about this one, that cracking code is this. And it is true, this one is like the most fundamental one, but then you have to make a lot of assumptions. If you are making a lot of assumptions, the search space becomes kind of like big, and it's a lot about human engineering. If you are kind of in that space, it's more about engineering. Like you can engineer your process to be more efficient and kind of automating a lot of tests. And with those two methods, even more, right? So the thing is that for known algorithms and known keys, you can pretend to be doing that because you control everything. And then you can see, like initially what you do is you're taking a known algorithm, you're assuming you're assuming certain keys, and then you can do this fully at free will, and then you're analyzing the statistical properties, you're observing them, you're learning what they look like. And then once you do that, then you can go back and see with those statistical properties that you discovered, can you break the code? Can you, given, like, let's say this, can you break it, right? So normally what happens is the scientists kind of start with this, because they have the algorithm, they have everything controlled, and they encrypt a lot of stuff, and they observe how the ciphertext behaves compared to the key and to input data, right? They collecting a lot of statistics. So they basically doing this, collecting a lot of statistics and observing like how it deviates from randomness, right? So every time you have something which deviates from like 50-50 chance, there is an information leak, right? Like if the algorithm is perfect, then you have just 50-50 chance. Like there is now no extra information leak. But if there is, then you can kind of exploit it and you can calculate your chances, right? So if like 49% of the time that leads to this, then you have this 1% of extra thing that you learned already. So when you're guessing, like when you're making a hypothesis and you're guessing, okay, what is it, this character or this character, you already have like 1% higher chance because you've discovered that leak, right? So it kind of accumulates. And because in computing, you're processing data like multiple times, many times, that your results compound, right? So if you have just slight small leak, then you can kind of magnify it, and eventually it will crack. All right, how are we doing with time? Yeah, maybe a few more minutes. So then with the brute force attack, we're trying all possible combinations, and we are basically a bit dumb. So we don't care about being smart. We just care about being efficient. So we're gonna use GPUs, we're gonna use massively parallel computing, and we're just gonna go for it, right? We can crack certain things by accumulating knowledge of how far we've tested some things, and we can store the partial information to not repeat the same calculations again, right? So there are certain things, especially, for example, for cracking hashes called rainbow tables, and they are used for like building up enough knowledge that you can crack longer and longer hashes, right? It's the most basic attack, and it is proportional to the key size, and it assumes that once somebody cracks, it understands what it is that that they got, right? So let's say I'm cracking something, and I assumed it's in English, but it isn't. Then I'm gonna miss it. I'm gonna hit the correct key, but it's not gonna be in English, right? So that would be a bummer. So I have to assume that when I find the correct key, I will see that it is a correct key. I have to have some metric telling me, yes, that is the key which is actually solving your puzzle, right? So for example, if you are cracking a binary hard drive dump, which is full of images, and you're waiting for English text to appear, that's never gonna happen, right? You're gonna hit the correct key at some point, but it does not gonna give you an English text, right? So you have to know what you are expecting to get out, right? And you have to recognize it, that yes, I got it. Like now I can see this sequence of bits is actually a JPEG image, right? So otherwise you're not gonna be able to do this. All right, so then brute force search spaces, depending on the size of the key. Those slides were prepared ages ago. I honestly am scared to think how long ago those slides were prepared. But back then, 10 to the power of 6 was like orders of magnitude more than what we were doing at the time with computing, right? So those statistics are with the assumption that you're doing 10 to the power of 6 decryptions per second, right? So I was a little bit worried that those slides are actually not accurate, so I checked. And surprisingly, currently we are at around that level right now. So today, some like data centers and the biggest like GPUs can do a couple of those, right? So the slides are not too off, but they are not super safe anymore. Like we probably would need to add maybe 2 or 3 to that number, because 10 to the 6 is already something we can actually do, right? So with this assumption, you can see that cracking like a 56 bits key, it's gonna take 10 hours, right? And that's like really doable. And probably with modern computing, maybe even faster. But cracking like a 26 characters permutation is gonna take like 6 billion years, right? So even if we multiply it by, like, divide it by 6, so it's about 1 billion years. So it's not bad, right? It's still pretty good, even with the current speeds, right? So if you have like a 26 character long password, and it's based on some sort of permutation of the like the mechanism which encodes the encryption algorithm is used on permutations, then it gives you like pretty solid security even today, right? So this 10 to the 6, I don't know what people use these days as a kind of a metric for how many decryptions per microsecond can you do. Those are per microseconds, right? This is not per second, it's per microsecond. So that means you have to multiply it by another 10 to 9, right? So you can see that with the key sizes, with the reasonably small key sizes, we are in a reasonably strong kind of computational security regime. And this is another one, time to break. And with the 200 bits key, it's like 10 to 40 years. So it's a pretty long time. Even if we add maybe 2 orders of magnitude, that drops a little bit, but it's still like, comfortable. Okay, so let's have a break. And then we will do Caesar. Time to break, yeah. I will stop. So there is a tool which translates characters from one set to another set, and you can use it for Caesar ciphers to sort of convert. So I'm converting the word security, and I'm converting all the letters between A to Z into the letters between D and Z and ABC at the end, right? So I'm kind of wrapped around. So it's I shifted everything by 3, and then the characters are like this. So S becomes V, E becomes H, and C become F, and so on and so forth, right? So I can kind of test my Caesar ciphering of the word security, and I get this sequence. So there was a typo because it was wrong, like here, the LW were missing. B was okay, but LW, I don't know, Control G or something happened, and it was messed up. So if I regenerate this, it will be corrected. No, it's perfect. Now it is corrected. Right, so let's continue. The first one, we are diving into a very simple substitution cipher, which is a Caesar cipher. And as we discussed already, we already know it. It shifts the alphabet one way or the other, and then you have this sort of replacement going on. So we shift all the letters like right-hand side, and then they become kind of higher in the alphabet. The alphabet wraps around. So if we have something towards the end of the alphabet, it kind of wraps around and uses the early characters. So if we represent the letters with integers, what is the key? Yep. Yep. So the key is +3, or for encryption, and for decryption -3, right? So the encryption decryption is the plus or minus operation, and the key is 3. What are the encryption decryption functions? plus and minus, super nice, super easy. Enhancement possibility, shuffle the letters arbitrary. And then we have a monoalphabetic cipher, right? If we shuffle the letters, then we have an arbitrary substitution going on, right? But we have to know the key, which is 26 characters long, right? Because we need to know the order of the characters. Right now, we don't need to know the order because we can reconstruct the order by the key, which is just a number. But if we do this monoalphabetic cipher, then we have to have a key of the length of 26 characters, right? So what is the total number of keys for the Caesar cipher if we're doing the normal one without the enhancement? How many possible keys can we have? Yeah. So 26. Can we have 26 or 25? Yeah, because 26 is the same as the 0 one, right? It kind of wraps around. Yeah, good. Then we know that substitution ciphers have a flaw. The flaw is that in English, we can do text analysis and we can discover that letters are not uniformly distributed, right? And if the letters are not uniformly distributed, they leak information about the frequency of the letters. And letter E is by far the most common in the English alphabet, or not alphabet, in the English texts. And then it followed by T, R, N, I, O, A, S. So if we know this, and if we have a ciphertext, we can run a statistical analysis on the ciphertext and assign with high likelihood that the most frequent letters from the ciphertext are probably E, T, R, and so on from the English text, if that ciphertext is an encrypted English text, right? And then some letters are very rare. And also we can analyze the text and say, okay, if those letters are very rare, they probably in this. So we, instead of doing a brute force, we already are doing much smarter, right? We are not exhaustively searching everything. We just kind of playing some tricks to reduce our search space. And then we can have tables for pairs of letters and triplets of letters, and then analyze statistics of that as well. And that will leak information into the ciphertext too, right? So unfortunately, the monoalphabetic substitution ciphers don't change that. The situation is still quite bad, right? Even if we do this trick, even if we do this enhancement and really shuffle the letters and use like an extra key, which is the 26 characters long, it will still suffer the same statistical attack properties, right? So possible enhancement, use more alphabets to guess and flatten frequency distribution. And this is like a polyalphabetic cipher, which means our letter maps not to a single character, but maps to possibly two characters. And then we're gonna introduce this extra complexity, right? So now when we, let's say, so we have those two situations. We have the plain text with the characters, and some of the characters are very highly frequent, right? So let's say those are like highly frequent characters, right? And then we end up with the substitution cipher text. So there is a substitution cipher going on, which leads to the ciphertext. And then in this ciphertext, that character and that character will appear a lot of times because it follows the frequency. So the frequency histogram of this text, so if I have some sort of histogram and I kind of calculate it here, I will have the same, right? So what we can do is we can say, okay, we have a problem, like those bastards leak some information, right? So what we can say, okay, because here we have this substitutions, which says this character maps to this, this to this, this to this, or this. We can introduce two characters, right? And suddenly one of them is being like 1 or 2. 1 is used here, and 2 is used here. And suddenly the high frequency of that one character, which was high frequency here, goes really down because, like, not really down, but it halves, right? Half of it becomes this and half of it becomes this. So we sort of are leveled up. We can play this analysis and actually try to level it up such that it's sort of even, right? It's all close to even. And then it does not leak information. So we can use polyalphabetic cipher in such a way that we're introducing additional characters in those high frequency characters such that we are trying to flatten the histogram, right? So that's what happens with this cipher. This cipher kind of introduces this additional alphabets, and then you have the flattening of the frequency distributions. In fact, you can make it such that low frequency in English suddenly appear to be high. So you can kind of throw off the investigators into a blind alley, right? So this is the frequency distribution for English characters. And you can see E is really stands out. It's much bigger than B, for example. B is not that frequent. Q is almost not used at all. And then T is the second biggest. So E and T, right? So E and T are quite interesting because the word the happens quite often in English, and T and E are very frequent characters, right? So if you analyze a ciphertext and you see pairs of very frequent characters, you can kind of guess the one between them is probably H, right? Even though H is not very frequent. So H is there, like it is kind of frequent than most, but it's not like on the top 3 or top 4. But still, you kind of see that this the appearing as a pattern, and you can sort of guess certain things. Okay, so then how to encrypt with the polyalphabetic cipher? You have so this particular one is not using the multiple alphabets. It uses a pattern where we, like, the normal substitution cipher has each character maps to a substitution, right? So this character maps to substitution, and it kind of, the properties of the plain text are kind of reflected in the ciphertext. But what if we have a key which is repeated, and then it's like, let's say ABC, like A does not always go to the same character, but because it depends on what is here. If here is A, maybe it goes to B, but if I have A and, oops, I have A here, and I have A, B, C, D, E, and now I have A with D, maybe that goes to C. So I'm kind of messing up with the frequencies of the characters here because I have a certain cycle, and then I repeat A, B, C, D, E, A, B, C, D, E, and so on, right, along my plain text. And I'm doing this substitution, but it kind of combines two characters. So then the A in the plain text does not always goes to B because sometimes it goes to something else. And again, I'm messing up with the frequencies, right? So this particular one, is using the word deceptive. And then we discovered save yourself is our plain text. And we are mapping letter by letter and we're doing the transformation, right? So we know that like usually what happens is you convert them to numbers, convert these ones to numbers, you add them together, and then you do modulo 26 to get like back into the alphabet, and then you sort of know like what you should do, right? So you if this one goes a little bit further, you start again deceptive, right? So what you can see, yeah, so it's sort of like M monoalphabetic substitutions, right? Because we are multiplying the length of this one through the letter. So it's kind of like a cyclic substitution. Sorry. So this one has some problems. One of the problems is you can try to find a repeating pattern in the um, in the so let's see. No, I kind of don't see immediately pattern, but what you're trying to find is you're trying to find some repeating combinations of letters, and you're trying to see if that repeating combination of letters, like what is the distance between the repeating combinations, and you hypothesizing that the distance is somewhat related to the length of the key. Because what we want to do, like first thing that we want to find is we want to find what is the length of the key that has been used, right? If we know that, we can brute force the search. If we don't know that length, then brute forcing all possible lengths makes much harder problem to track, right? So what the first thing that we would like to sort of reduce is we try to reduce the search space by observing if we can find some sort of okay, there is, I found it. So TW, for example, right? Yeah. So if you find a pattern, you can try to count. So if we try to count between TW, so we say 1, 2, 3, 4, 5, 6, 7, 8, 9, and we say, yeah, we have a strong suspicion the key is probably 9 long, right? And if you count, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So you already know the length of the key, right? I mean, we don't know for sure, but we have kind of a hunch, or we have some statistical evidence that that's probably correct, right? And then we can brute force keys of length 9 and try to crack it, right? All right, so those are two examples of substitution ciphers. And now we're moving into permutations and transpositions. So I showed you this yesterday, where we have, we write things like in rows, and then we, what is this one? This one is messed up. Uh, No, it's not messed up. It's fine. We start with the key, and the key says, okay, read column first. So we have T, T, and A as the first four characters, and so on. So we kind of we wrote it in this sort of a matrix way, and then we are not reading one by one, because that would be like too simple to decode. Like if you always start with the first column, it would be easy to transpose the text into the correct order. So the key is the order in which you're reading the columns, right? And they are shuffled. So we're starting with this column, then with this column, then this one, then this one, this one, this one, this one. And then without the key, you don't know like how you should like transpose the text back to the original shape, right? You do need to have this key to know where the TT and A go into. And also you need to kind of know how big is your matrix, because is it like every 4 characters, or is it like bigger, and so on, right? So you don't know the length of the key neither, right? So the length of the key tells you how big each like slice is. And then you know, okay, if I know the length of the key, then I know how big my slice is, because I have to divide this one by the length of the key, and then I know how many, like how long the chunks are, right? So this one is quite good. It retains the alphabet. It doesn't introduce any letters or any symbols into the text, but it is sort of cumbersome to permutate back, because you have to try out all sorts of different permutations of the column, and also all different permutations of the structure, right? Because if you only had 5, like now we have 1, 2, 3, 4, 5, 6, 7 columns. If you had 5 columns, it would be like longer slices, but the structure would be different, right? So this one is quite clever. And both of them, the permutations and the substitutions are used later for more complex ciphers. And an example of this one is called rail fence. And this is basically what is described here. So if you were to crack this one, you would have to first hypothesize how big is the key. And then you would have to multiply it by all the permutations of different orders that you have the slices in, right? There is not much not much cleverness you can do here. The frequency of the letters is following the English alphabet, because it's the same letters. You didn't change the letters, right? But you changed the order. And the frequency analysis will not necessarily like what it can do. It can tell you where some yeah, it does not really help you. Like you have the letters as they are. So all right. So then we talked a little bit yesterday about the block ciphers. So the block ciphers produce conversion from a block at a time, and then they produce the output block for each input block, and they reuse the keys, and they are the most common. They are super efficient for large volume of data to be converted, and the bigger the block, the more efficient they work, right? So if you need to convert like 1 terabyte file into an encrypted 1 terabyte, then you want to use relatively large chunks of large blocks, right? When you are formatting your hard drive, like for Linux, you have a choice of the block size, right? So you can decide how big your inodes are, right? And you can say, yeah, I want them to be 256 bytes or whatever it is that you want, right? You can say 32 bytes and so on, right? You have a choice. So when you format your hard drive, you have a choice how big the blocks on your drive are. And the reason for the choice is that if you're using a drive for storing like media, like video files, right? And all your video files are like bigger than or like 1 GB, right? So all your files are really big. Then you should go for really big blocks because the random access and reading and writing will be super fast. If you go for very small files, very small blocks, the reading and writing will be really slow. It will kind of use up a lot of effort to read and write from your disk, right? So for large files, it's much better to use large blocks. But if your files are very small, right, and you use the large blocks, what will happen is you are wasting space because in a single block, you can only have one file, right? So if I have 20 files and each of the files is, I don't know, let's say 5 bytes, right? So if I have this situation, then I have those blocks, I will use 20 times 256 for those 5 so actually my files occupy 100 bytes, right? That's my situation. But in this case, I'm using 20 times 256, right? In this situation, I'm wasting 20 times 32 bytes, right? So for storing those 5 files or 20 files with 5 bytes, I'm gonna use that one, right? So here I have a lot of used up space, which is empty because I cannot use it for anything else. And here I am much more efficient. It's more squeezed, like I have less leakage. I have less waste, right? So this is a more efficient, but slower. This one is less efficient in terms of storage, but much faster. So for bigger files, I don't care, like I'm not wasting so much space anyway, because most of my blocks are kind of used up for big files, right? But if you have a lot of small files, you should go for relatively small blocks. Maybe like even, like usually we don't say bytes, we say kilobytes, right? But 4 kilobytes is like some kind of like lowest limit that you can go. So it's the same for the ciphers. Like it depends what you're doing, and it depends what you need to convert to something else, and it depends whether you want the streaming or whether you want it to be fast on the spot, right? So for things to be efficient and fast and on the spot on your hard drive, then block ciphers are a win, and the bigger the blocks, the better. And then for if you want to produce inputs continuously, if you're streaming something, if it's a video or audio and you want to encrypt it, it's a phone call and you want to encrypt the conversation, then obviously you want streaming cipher. So they are converting one element at a time, and the advantage is it's like faster and you are more responsive. So there is a hypothetical example of a decoder which kind of takes input and then splits it into like 16 channels, shuffles them around, and then reconstructs the 4-bit output, right? So it's sort of like a cipher which kind of mangles up like a large dimensionality of the input and then encodes it back into the 4-bit output. And then to decipher it, you need to know this kind of what's going on here, and you can kind of reconstruct it, right? So we're not shoveling those 4 bits. Why are we not shoveling those 4 bits into like the output 4 bits directly? Why do you think? So I have 4 input bits, right? How many combinations are here? How many? 2 to the power of 4, which is 16, right? And then I have my output, same story. I have 16 combinations. So then if you say, okay, I have some sort of a conversion, I have some sort of mechanism M0, which does that directly, then this mechanism M0 converts 16 possible things into 16 other possible things, right? Correct? Correct. So now if we take this one converts 4 bits into 16. So like currently I have here, I have 16 bits, and here I have 16 bits, right? What is my search space for those 16? It's 2 to the power of 16. Well, it's a pretty big number, right? It's like pretty big number. And same here, right? So now my mechanism 1, so mechanism 0 is 16 to 16. Mechanism 1 is to the power of 16, right? And now you need to work out, like work out what's going on, right? How it works. You don't know, you're guessing, you are cryptoanalytic, right? You're sort of looking into statistics and you're trying to work out. How long do you think it's gonna take you to work out this one, 16 to 16? Pretty easy, pretty straightforward, right? How about this one? Oh yeah, this one is like a mess, right? It's like, okay, we're probably not gonna be able to do much with this. So that's why we're doing this. That's why we kind of saying like, let's expand the search space such that this mechanism is so complicated, it's very unlikely anybody's gonna work out what's going on, because the search space is so huge. We're gonna have a lot of noise and a lot of like things going on, and it will be much harder for anybody to investigate that than to investigate that. So we're doing this sort of expansion of dimensionality from 4 bits into something really massive and really kind of complicated. And then we have the encoder. The actual encoding is deterministic. Like we always convert the 4 to 16 and 16 to 4 in the same way. We have some sort of a deterministic way, but what's going on here is like the key, like it's the complexity which is introduced to make it sort of untraceable. So block ciphers look like an extremely large substitution, right? So basically we have those large spaces which are sort of substituting from one space to another, right? So in the normal alphabet, we had 26 characters into 26. Here we have like 2 to the power of 16 into 2 to the power of 16. It's like a massive amount of substitution possibilities, right? And then if we have a block cipher of n size, that's what's the number of possible plain texts. So if we have a block cipher of size n bits, what is the number of possible plain texts? Yeah, that's what we did, right? It's the 2 to the power of n, right? So if I have a cipher of n bits, that means I can convert like 16 possible things into 16 possible things if the size is 4. How big is the substitution table and what is the maximum number of reversible mappings? That's what we're after. So that's why we're doing this expansion, because then the number of reversible mappings and the search space is kind of exploding if we're doing the conversion, right? So what constitutes the key in the encryption schema? What would be the key in this one? So we have to map each of the outputs to one of the inputs, right? So we have to say which bit goes to which bit. So we have to do this mapping. Like we have to say 1 goes to this goes to this goes to this, right? So how long it's gonna take us? Like, what is the representation that we could use to do this mapping? So how many, like, we basically have to do a mapping, right? So we have to say 0 goes somewhere, right? And this somewhere is a number. How big is that number? How big is the destination number? So the number is from 0 to 15, right? So it is 4 bits that we have to represent. So from 0 to 4 bits, it's like 4 bits, right? Do we need this 0? We kind of don't need this 0 because we can say we always go from 0, 1, 2, 3, 4 up to 15, right? So we don't need the entry numbers. We only need the sequence of numbers which represent where that number goes to, right? So it's 4 bits for 0, 4 bits for 1, 4 bits for 2, blah, blah, blah. So it's basically 16 times 4 bits, right? What is 16 times 4? 64. So 64 bits. So we can represent this table using 64 bits. Our key is 64 bits long to represent that table, right? You agree? Yeah. Is it practical? Sure, it's practical, like 64 bits, but we only encoding four bits at the time, right? So we have an encryption algorithm which takes 4 bits. It uses a 64 bits key and encrypts them and potentially decrypts them, right? 4 bits at the time. Yeah. So then there is this confusion and diffusion concept. It's a little bit complicated. So what we want is like a cipher needs to completely obscure statistical properties of the original message, right? So which cipher so far we learned to provide this? Was the substitution messing up with the statistical properties, or was it the permutations? The permutations, right? Because like permutations did not care about the statistical properties. So, and then the guy Shannon again suggested combining substitution and permutation to obtain diffusion and then confusion. So diffusion is that a plain text bit influences many ciphertext bits. That's what we did here actually. Oh, oops. Right? So we know that this bit is kind of like potentially influencing all the output bits, right? Each of these guys is potentially influencing all of those, right? So one change here changes all of them. One change here changes all of them, and so on, right? So it's not like, okay, if I change here, I have here change. If I change here, I have this. That would be really easy to work out what's going on. Like this one, like I change here, everything changes. I change here, everything changes. So it's like much more difficult to work. So this is the diffusion part. The diffusion, that each bit influences many cipher bits. And confusion is the relationship between the key, like this, this key and the ciphertext. So we want this one to influence many things here, and we want this thing to not have much relationship to any individual things here, right? So the diffusion is sort of like we diffusing information from here to diffuse it there, and confusion is we want this to be not linked to any of the particular ciphertext. It's a little bit of an abstract concept, but it has those very practical implementations, and there are very they actually use the terminology like confusion and diffusion matrices to introduce into your ciphers to introduce those properties, right? So here we have the key bits which are mapped into the ciphertext bits and how they are kind of influencing it, and then you have this sort of permutation which is used to kind of rearrange things and reshuffle the bits such that it kind of creates the confusion. It does not link directly to the way the bits are calculated, right? So I mean, if you kind of think about it, like if you analyze it, it kind of clicks, but it's a little bit abstract initially, right? What we want to break some information leakage. We want to break some patterns. And one way of breaking the patterns is when we calculate something, we reshuffle it. Like we have another mechanism which kind of reorganizes it, permutates it, right? So one mechanism is to substitute, another mechanism is to permutate. And we're combining both. We're combining substitution and permutation to sort of do this transformation. So in here, we're doing substitution, right? We're doing like this bit is doing substitution. And then in the encoders, we can reshuffle the bits, like the final outcomes, that we don't make a direct mapping, linear mapping, but we do this sort of a permutated mapping. So you can see how the bits are being like mangled in such a way that it is, we don't like read them linearly. We kind of introducing this additional stage, right? So people worked on it kind of on the information theoretic basis, and they worked out those operations and the matrices, and they kind of played with it until they got something that was kind of solid and difficult to break. So then IBM developed initial cipher in late 80s. And then it was sort of revamped and updated. And eventually they introduced like 64-bit plaintext block with a 56 key, and then 16 rounds of doing this sort of doing this, right? Because we need 16 rounds to go 4 bits at a time to get to this 64 size of the block, right? You understand this? So we're doing 4 bits at a time. We have 64-bit blockchain and block. So we need to repeat it 16 times to actually do the full block. But the key is not 64. The key is 56 because we use the remaining 8 for like making sure that the we have a certain like internal consistency check, and those extra bits are not part of the key. So 56 bits are really random and really like the randomness that secures your protocol, but the remaining 8 are calculated, and they are part for doing this transformation, right? So the key is not exactly the same. We're not doing like one-time path type of situation. We're doing something else. We have a 56-bit key, which is used for those 16 rounds. And then the missing 8 bits are kind of calculated when we're doing those rounds. Does that make sense? Abstractly speaking, yeah. All right, so then it was an incident in 98 where the 56-bit key of DES was actually cracked. And then we knew, okay, the key is too short. Like we are able to crack it, so it is really bad. Like we have to find something better. So the 56-bit key was probably brute forcefully cracked because the crypto analysis of this algorithm does not actually leak information in a way to really help with cracking, but the technology got good enough for brute force cracking. Therefore, we kind of knew we have to move beyond 56 bits. And then if we go to this 56 bits, we can see it is kind of, crackable, right? We are sort of in a regime that says, well, in a couple of hours you can crack it, right? So that's not good place to be. So 56-bit keys is a historical artifact, not usable anymore, and not really usable for a long time, right? It has been 98, and back then they stopped being usable. So now we can go into like a really nitty-gritty details of how the rounds are done, but you have to be a little bit motivated to do that, right? So if you really want to go into the cryptoanalytics side of things and you want to really understand the nitty-gritty of how the bits are flowing and how they are calculated, you can do it. For everyday life, you don't really care on that level. It's sort of like learning assembly for programming, right? Normally, you don't really care. So if you really want to go there, I encourage you, but I am not gonna go all the way down to like how things work under the hood, because it is a little bit like technical, and I don't think you will kind of benefit from it. So there is like and also the slides may not necessarily be the best description of how the rounds are done, but there is a certain amount of processing which goes on the bit level with functions like XOR or permutation or like parity kind of reordering. And then you basically kind of are calculating things and like reusing some parts of the calculations. And then you kind of have shifts. You're shifting bits like left or right by certain numbers. You're kind of doing the XOR and you're calculating it. I don't know if like yeah, we have to go all the way down. So how are we doing with time? Right, so we should have another break, and then I will kind of go into the there is one thing that I have to talk about, which is the meet in the middle attack. Why this cannot be used twice? You have to use it 3 times. So that's an interesting discussion. And then there is one discussion for there was something for the modes. Yeah, we kind of need to talk a little bit about the modes. Those are a little bit higher level concepts. Like there is quite a lot of really detailed discussion of how the bits flow. And as I said, like if you really want to do something in that space, you kind of need to immerse yourself into the bit operations. But for most of you, it's probably too much detail. So and it is too much detail for me as well. I never worked on that level. I sort of get a feel and understanding of how things work, but I think it's like a very specialist and very niche domain that works only for those people who are actually doing the crypto analysis, right? So let's have a break. And then there are like 2 or 3 more topics that we have to cover, and then we can do some more practical things. So timer, 10 minutes, 5 minutes or 10 minutes? All right. All right. Oh crap.